Okay, hi folks, and welcome to our second online machine learning meetup. And thank you to Matthew Nicholson from Adapt for organizing all of the logistics and the vision mixing and all of that. Machine learning meetup. And thank you to Matthew Nicholson. Okay, and so we have a great lineup tonight. To kick us off, we have Facebook's Kavya Srinet. And she'll be talking about NLP and Minecraft, which is very interesting. Yeah, so the echo actually could be me, but I don't want to get rid of the wrong. I don't want to mute my wrong thing. So let me just close my. Okay, so what I've done, I think it was because I had my YouTube window open, possibly. So without further ado, so second up we have Chris Hokamp, who did his PhD actually in Adapt and DCU a number of years ago, and is a research scientist with Alien. And welcome back, Chris, because at our inaugural machine learning meetup in January of 2016, Chris was one of the first speakers at it. So it's it feels like you're coming home to speak again at this event tonight. And then we have Sebastian Ruder, who is with DeepMind in London. And Sebastian is going to talk about cross-lingual transfer learning and NLP. So thank you for all three speakers. And without further ado, I'm going to hand over to Kavya.
Yeah, hey everyone, I am Kavya. I'm a research engineering manager at FAIR, and today I'm going to be talking about the Minecraft project that we're working on at FAIR. So this is a research project that is aimed at building an assistant using the game of Minecraft as a test bed in order to facilitate the study of agents that can complete tasks specified using dialogue, and eventually having assistants that can actually learn from these dialogue interactions. So today I will be describing the tools and platforms that we've built so far, allowing players to interact with these assistants and to record those interactions. And I'll also go over the data we've collected so far in the process. In addition, I will be demonstrating and describing an initial agent from which we and hopefully others here in the conversational AI community can iterate from. So before I start with the talk, I want to show you a demo of the assistant that we have right now to give everyone here an idea of what Minecraft is, to show what we've done so far, and to demonstrate the space of things that we're attempting. So I will be just switching over my screen and going to Minecraft. So this is Minecraft. I'll log in to my server. And okay, so this is Minecraft. As you can see, it's an open world sandbox game where people build and craft things. It's a very simple environment with huge variety of interactions possible with the environment as well as other human players in the game. It has a simple physics and a very simple block ID vision. So like I said, everything is a single block. The game comes with a finite amount of atomic objects like these single blocks, like lots of block types. And as I show you a demo, you will be also seeing like lots of mobs like ducks and cows and pigs moving around in the background. That being said, it is also a very popular game. So it had about 91 million monthly active users. And people build all sorts of incredibly rich structures in this game. So we have decided to leverage that and even use this environment. So our assistant, as you can see, appears as another human player in the game. And you can speak to it using the chat box in game. I can, for example, ask it to come here. Note that what happens when I tell it to come here is there is a neural semantic parsing model that takes in this language and converts it to a program that can be executed in the environment. I will be talking more about that. So let me just point somewhere and ask the bot to build a red cube there. Going back to the semantic parsing model, it takes in this sentence as an input, and then it converts it to a program saying, okay, so it's a build, and the thing the user wants you to build is something that has color red for some definition of red, and then something that is a cube for some definition of cube. And where the construction needs to happen is there, where the user is pointing at. So note that when the semantic parser actually converts it to this program, we also need an interpreter to use the information from the environment and actually convert it to a program. So when I say there, it knows what there is. We've leveraged the crosshair in Minecraft quite a bit. So you can, for example, point at something and ask it to destroy that. This is, again, the parser tells it that here, convert it to a destroy action and destroy the thing that is present at where the user is pointing at. So the bot also understands the concept of loops. For example, I can tell it to make 2 squares there. Note that this is make a square there, but like 2 times in a row. Again, the semantic parsing model, or the natural language understanding piece, basically tells it that do this twice, and then the interpreter resolves it into the things, and then the bot actually executes it. Now I'm going to tell the bot to, for example, go between the squares. Oops, go between the squares. So the bot understands some sort of, so for some definition of between, it went between the squares. That being said, I wanted to demonstrate that the bot understands relative directions. So for example, I can ask it to build a green circle to my left. So to my left will be first find where the user is standing, and then compute left of the user, and then build a green circle. So as you can see, the bot also has a concept of a memory. This is a triples sort of SQLite database at the moment, which comes pre-populated with certain things like certain shapes and certain colors. But the idea is it'll get better and better at this as humans play with it. So for example, you can point at something and ask it, what is that? Let's see, sometimes it'll tell you, yeah, now it's telling you the actual properties of the blocks that the circle is made of. But you can also sort of, point at something and ask it, what is that? It queries in the background, the semantic parser tells it that here, that is a question about something, and then the interpreter actually accesses the memory and gives you the answer for it. Okay, so then you can sort of, again, to demonstrate loops again, I can ask it to dig 3 tiny holes there. So then for some definition of a tiny, which are heuristics, by the way, and for some definition of a hole, the bot will dig 3 tiny holes there, as you can see. Now I can point at something and be like, fill that hole up. And so for the hole that I'm pointing at, it will resolve it in the environment, which is what the interpreter does, and then the bot will execute the fill action. Okay, it did not fill it. It does fill, I promise. Okay, so for now, I'm going to ask the assistant to make a house over there, and we'll come back to the demo if we get time to demonstrate the perception component. So let's go back to the presentation. So the goal here is, the idea is to always have a functional assistant. And by functional, I mean all the way from language to execution of what you said in the language in the environment. We want the bot to be fun to play with and fun for humans to teach. So hopefully the mistakes it makes along the way will be amusing enough for humans to keep coming back. Now I'll talk a bit about the scientific goals. So we want to, on a high level, integrate memory, multiple modes of perception, and reasoning into a full useful agent. For reasoning, I want to go back to the point of language understanding component. So if you remember in the demo, I showed how when you say something, there is an understanding piece. It's called semantic parsing and natural language processing. But the idea is it takes in bag of words, language's input, and converts it to something that is, an intermediate representation for the system or the assistant. Then we have memory, which the bot uses to refer to and understand things, as I showed in the demo. Then there's also perception. We haven't talked about this much, but the idea is this is something that the bot uses to understand parts of objects. And on a high level, we want to study about the synergies of these components and synergies of machine learned and non-machine learned or heuristics components, as I mentioned in the demo. We want to be able to specify tasks and give supervision using language and not just direct labels like that is a cat and that is a dog. So we want to overall understand how we can make an assistant that can improve itself by learning through humans, learning from humans, and not just through direct supervision. So again, I want to reiterate that the goal here is to make an assistant that actually interacts with humans and learns from them, where the learning goes beyond direct supervision of labels and rewards. So to give you an idea of why this problem is hard, let's say the human says, hey bot, let's play a game. So when you say this, you assume that the assistant understands that game is this temporal aspect and is only valid for as long as you're having this conversation. Okay, and the bot says, all right. Then you say, every time I get close to you and say cow, you have to jump twice. So remember in Minecraft, I mentioned cow is a moving object or a mob in game. So you're redefining the concept of a cow. You're assuming that the assistant understands the concept of getting close to something and getting far from something. And then you associate this whole thing with an action. The bot says, okay. And then you say, if I say pig, then you have to follow me, but really slow. Again, you're redefining what a pig means, but you also assume that the assistant understands what going slow and fast means. And the bot says, okay. You said, okay, bot, that was fun. Let's call that game cow pig. So now you went back and named the entire game. And the bot says, okay. So this is just one example of a difficult scenario, but you can think of lots more. Like, for example, around the corners of every cube, that I made. So yeah, so the basic approach that we've taken so far is we don't shy away from bootstrapping components. So we start with heuristics and scripts for things, and then slowly as we get more data, we start turning them into machine learned models. We did some human interaction studies where we asked people to play with the assistant, and then that's how we sort of define the distribution over the action space that the assistant should be attempting at the moment. We want to release agents, make them play with people, and the hope is they will get better as they play more and more with people. To give you a sense of where we are right now, we've open sourced the platform. So the code and data is available at Facebook Research/Craft Assist. The assistant itself has its core as a neural semantic parser, as I mentioned. This is a model that is trained using BERT encodings for the language side and treating this as a sequence-to-sequence problem. This model has been trained on using language from composable templates. So we wrote thousands of templates to start with. Then we showed them to humans and asked them to rephrase the language to make it sound more natural. Then we got a lot of data from humans just playing with the bot. So we have tools in place that I'll talk about later that sort of use crowdsourced humans to get us logical forms or these programs for free-form text. We have a symbolic memory, which is a relational database that you can read from and write to. And then there's a basic perception system. And so overall, there's a high-level action interface that sort of ties everything together and enables the bot to perform actions in the Minecraft environment itself. In terms of infrastructure, we've done a lot of work. We have the infrastructure in place where absolutely anyone with a Minecraft license can interact and play with the assistant. All the server events are automatically recorded in order for it to be used as training data to better the bot. In terms of labeling tools, this is really interesting work, and this is what we're doing right now as we speak. We have designed and implemented a semantic parsing tool that can annotate free-form language to logical forms using crowdsourced workers. So this enables us to get ordinary humans with no knowledge of domains at all to be able to write these programs for us in order for us to be training models on them. We are working on bot annotation tools as we speak. What this means is, if you remember the demo, I told the bot to do something and the bot would do it. But like at no point I could give it supervision or actually tell if it made a mistake. So as we speak, we're working on tools through which humans can provide richer supervision on what went wrong with an assistant if it made a mistake, in order for the humans to be able to visualize where in the pipeline of execution the assistant is, and in order for humans to be able to teach the bot new concepts. So for example, if I understand that the bot can move, maybe I can teach it new concepts like flying, and these tools will enable that. So as we speak, we're working on these. I won't go into the details of this slide, but the idea here is to demonstrate that we've built a grammar. We handwrote about 4,000 templates to convert this grammar to surface form. And this grammar is actually pretty composable. It has a lot of coverage. So it covers about 90% of the things that the humans said to the bot. And it can support sequences of actions as well as it's really compositional. So if you look at this, this is basically a nested action dictionary of, a build can have a schematic and a location, and the location itself can have a reference object. So this is very compositional. So the idea of this slide is to show that this is what we're currently managing. It's manageable, but complex enough for a machine learned model. Perception, yes. Now let's go back to the demo and see if the bot built a house. And it did. Okay, so I told it, if you remember, I told it to build a house. And now I'm going to ask it to destroy the roof. And let's see if it can do this. So the idea of perception is that there are models. Yes, I need this. So if you saw, it understood that a part of a house is a roof. So the idea of these perception models are that they take in the environment and then they understand certain parts of objects. So going back to the slide, we collected about 2,500 houses that were built by humans in Minecraft, and the build order there is recorded. We have a 3D coordinate that sort of helps the assistant understand parts of objects like the trunk of a tree or the roof of a house, as you saw. And if you remember in the demo, I mentioned relative directions. So when I say left of me or between those, these are heuristics right now. But as we speak, we're training neural models that can handle the relative directions instead. So that's sort of where we're at the moment. But longer term, eventually, we want to get to a place where we can replace each scripted component of the piece with a learned model. It's one-turn interaction right now where you tell the assistant to do something and it does it. And sometimes it asks for clarification. Like when I said destroy the house, it asked me for a clarification. Do you mean this? But when to ask clarification is scripted at the moment. We want to turn that into a machine learning model eventually. And we want to overall close this loop of language, perception, and memory, as I mentioned. So the bot, another thing we are working a lot right now is this within session improvement of the bot. So the bot can learn in session on the fly from humans. So that was it. That was my talk. Thank you so much for listening. The code and the data is here. Here are a list of papers that came out of this work so far. And if you're interested in this kind of work, please feel free to reach out. We're more than happy to collaborate. Thank you.
Great. Thanks, Kavya. That was great. Really interesting stuff there. Perception models and semantic parsing and so on. I'm just going to flick over to YouTube and see if there are any particular questions. Let's have a look here. So we've got one from Jenny Ajarian. Does the bot learn from direct feedback from the user? E.g., you say, no, bad bot, do this instead, and does it update? Does it learn, I guess?
Yeah, so that's a great question. And that's what we're working on right now. So right now, in the current state of the bot, you can say no, and it will record it to its memory saying, okay, this is a negative signal for what I did, but it doesn't really implement anything. But the tools that I talked about in the talk will enable you to do that. So you can sort of tell the bot that, no, that was wrong, and that's sort of, and then you can also sort of, the tools open up another direction of, you can also, for example, tell it, where in the pipeline did it make a mistake? Was it the semantic parsing model? Did it not understand your command, right? Or did it understand it and couldn't execute it in the environment, right? So yes, no, it doesn't do it right now, but yes, it will be able to do it soon.
Cool, great, thanks for that. And then Trip Fisk asks, why is Facebook playing so much Minecraft? Work, right?
This is a research project. It isn't Facebook playing Minecraft. It's mostly us. I think this research direction actually goes beyond Minecraft. This can be applicable to any assistant, right? In the idea of if you have an assistant, can you teach it and can you make it better the more you interact with it? So the research itself, Minecraft is just a test bed for us right now because it's a rich and very simple environment. But the research direction actually goes beyond just the framework itself.
Mm-hmm. And actually, Kavya, just a question for myself. With the recent acquisition of Mapillary by Facebook, I know Mapillary had a quite extensive data annotation and labeling and segmentation tools. Is there any potential synergy there with your work?
I think so, yes, absolutely. And that's where we're going right now, to be honest. Like we do want to go into these end-to-end annotation tools because we figured that going through dialogue is one way, but starting with dialogue is hard. But if you can make user-friendly tools through which, one, it's easy for users to provide supervision, and two, it's users generally optimize for faster feedback as compared to talking to the assistant over and over again, really trying to explain it. And there's less number of sort of point of failures in using annotation tools. So I think, yes, we are definitely going along that route.
Cool. There's a final question from Nishtha here. Is it available in a different language or is it just English?
It is just English for now. It is only English. The semantic parser has been trained on English language only. So yeah, right now it's just English.
Mm-hmm. Cool. So that's all the questions for now. So Kavya, thanks a million for that. It was a super interesting talk.
Yeah, thanks for having me. I'm really glad to be able to speak at this.
Oh, cheers. Thank you.
Yep.
Okay, so next up is Chris, a few minutes ahead of time, actually. And so as I said earlier in the introduction, Chris spoke at our very first machine learning meetup over 4 years ago. And he's currently a research scientist with Alien in Dublin. And he's going to talk about dynamic ensembling for multi-document summarization and beyond. And he's included the link to the archive publication actually in the meetup advertisement. So, Chris, if you're ready to go.
I think you should be able to see my screen now.
Yeah, that looks great.
Cool. Okay. Well, thanks for having me. And that was a super interesting talk from Kavya. It's really cool. It's going to take me a while to digest all that, though. So this work is kind of, it's ongoing work, but we finished the first iteration of it, I guess you could say. And what we're working on is multi-document summarization. So I'll give an overview of what that means. And then we came up with a rather simple approach that we think is generalizes well, and it's appealing because of its scalability properties, and also just because for summarization in particular, it performs well. So this is joint work with Damien, Nia, and John at Alien. So just a quick outline of what I'm going to talk about. I'll go through this stuff pretty quickly. So I'm just going to overview multi-document summarization, what that means, and then quickly talk about the pre-trained transformer models that have recently achieved state-of-the-art in most NLP kind of benchmarks. Then how ensembling is relevant here, and then I'll introduce dynamic ensembling, which is kind of the new part of this work. So multi-document summarization is really just an extension of the summarization task in NLP, which is take a document and effectively compress it and try to retain the key information. Importantly, what the key information is depends on what you're doing. So that's kind of a underdefined task. But if we assume that you want to discard anything that's not central to the event or the topic that's being talked about and just produce a shorter document from a longer document, that's what we call the single document summarization task. So multi-document summarization, as you probably already guessed, is just do that exact same thing, but at the input, you have more than one document. And in the real world, this is a very common use case. For news is kind of a clear example where for a given event, it generates obviously more than one news article if it's noteworthy in any sense. So you have a cluster of news articles which are all about the same thing. And a common use case is to want to compress that cluster of many articles, it might be hundreds or thousands, into a single coherent summary, which would clearly be much shorter than the concatenation of all those articles together. And so this is the multi-document task. This is just a more concrete example of that. This is from one of the benchmark data sets called multi-news. So you have 3 source articles in the first 3 boxes, and at the end you have a summary of those 3. And the colors are just indicating that different parts of the summary were generated from different indexes of the input, so from different input articles. And now I'll give a concrete example from Alien's actual use case for this type of technology. So this is a screenshot from a coronavirus dashboard that we recently released, which is just built on top of our news API. And you see the clusters visualized by size. So these are different clusters that are automatically generated from news articles that are about the same event. And on the right, you can see the headlines for the news articles in a particular cluster. So the one that we're looking at is about Uber requiring its drivers to wear masks. And we have sources from all over the world. So these are being some of them are being translated into English if they're originally a non-English source, and then we're clustering them all together regardless of language. And so it's reasonable to think that we might want to, a user might ask, okay, what is this cluster about? There's different things we could do. We could just select a random headline as a baseline. We could look for the centroid in some sense. We could try to find like the central article that's like the most similar to all the other ones and give them that as a summary, or we could generate a summary from scratch. And so here's just a closer up of the cluster that we're talking about. So as I already said, our goal is to take all the documents and compress them down into a coherent summary. Some of the challenges here in the real world are that the cluster could be very huge. A given news event, if you take the global news output for that, it easily goes into the thousands of articles. The inputs might be drastically different in length. So they might contain very different content. One article might be a long format article from the New York Times, and others might be just a tweet that's providing, a tiny little nugget of information. And then the inputs can and do conflict with each other. So there might be information that is actually different between the inputs, and we might need to do some sort of, or we would like to be able to do some sort of automatic fact verification to be able to check and produce the summary that actually contains the correct info, or at least the consensus of the things that most articles agree on. I put the URL for that demo at the bottom of the page if you want to check out the demo yourself. So in the NLP literature, there's kind of two standard approaches to the summarization task that are called extractive and abstractive summarization. The extractive is the more traditional one, where you're just going to choose pieces of the input and compose the summary from little pieces of the input. So they might be on the sentence level or they might be on the phrase level, but your summary can only contain things that you observed in the input. And the more general case is abstractive, where you ask your model, your machine learning model, to generate a new summary from scratch. So in this case, it could generate anything. And this is a sequence-to-sequence problem. So the second one, abstractive summarization, is what we're talking about here. And I'll get into the details a bit now. So there's a fair bit of work on this already. A lot of cool ideas, and you might already have been thinking about, different ways you could build a hierarchy of articles, or have a tension between the different articles, or, all sorts of things you could imagine, crazy architectures. But when you have many articles, for one thing, that doesn't scale. And another thing is that your training data is going to be very limited in that case, because to train a powerful machine learning model, you need a lot of clusters of articles about the same event. So up to now, there haven't been data sets that are at that scale for this task. That's starting to change. And I think, maybe this year or next year, we'll see models coming out that train on, data at a much larger scale. And maybe we'll see really cool architectures for this. But anyway, regardless, it's attractive to be able to use a single document summarization model for the multi-document task with little or no change. And that's what this work is really about. I just pasted these two architectures from existing work, and there are others as well. All right, I'm going to do a brief aside on transformer-powered transfer learning, because that's what we're building on. This is just a couple slides. So a lot of people will have already heard of or used BERT, which is kind of the most famous one right now. And so what these models do is, at the pre-training phase, take in a bunch of unlabeled data and do a transformation on it in some way. So BERT does masking. GPT is a language model, so it tries to, given a prefix, tries to predict the next word. And BART is a fully fledged sequence-to-sequence autoencoder, denoising autoencoder. So these are effectively just different ways to, I think of it as different ways to unscramble the data. Your task is either fill in the blanks or unscramble the data at the pre-training phase. And these are pre-trained on huge amounts of unlabeled data for a long time on lots of GPUs by companies with the scale to do that. And then it's really cool that these models are now out there in the wild and released, and then you can just build your own stuff on top of them. So that's a key aspect of this work, where we build on top of the BART summarization model, or the BART model, which is fine-tuned for summarization. So this is a sequence-to-sequence denoising autoencoder, and we fine-tune that. These images are from the BART paper. So this is just a slide on the intuition behind fine-tuning. The idea is you take after the pre-training phase is done, you then take your in-domain data and you do a much shorter phase of training where you adapt the model to whatever the task is. This has been kind of the established thing to do in image processing for a lot longer than it has been in NLP. But with the advent of BERT and now the sequence-to-sequence models and several others, this is now also the state of the art for NLP is to have a pre-training phase and then a fine-tuning phase or a domain adaptation phase. Okay, so we're going to use BART in this work. And then we build on the Hugging Face Transformers library. And in the code base for this work also, you can use any model from Hugging Face that supports sequence-to-sequence generation. So just summarize the objectives before I go into the actual research section. So we want to use as much as possible the pre-trained single document summarization model. So we don't want to have any multi-document specific stuff in here. And that's for the scalability reasons that I mentioned before. So we want to try to just use the single document thing for multi-document summarization with no change. And as a part of that, we want to establish a baseline. How well can a single document summarization model do on the multi-document task? And there will, of course, be some tasks where multi-document specific architectures are needed. And so we want to understand that as part of this work. So I guess the key insight of this research is that you can use ensembling in a slightly different way than it's typically used. So the traditionally in machine learning kind of terminology, when we say ensembling, what people usually think of is the top image here. So take your input and run it through a bunch of different models or a bunch of different variants of the same model, and then at the output, do something with the predictions of all those models, reduce them into one thing, and that's your output. So your output is the combined prediction of a bunch of distinct models. We're going to kind of flip that on its head, and we're going to use the same model, but on distinct inputs. So for dynamic ensembling, our output will be a reduction of the output of the same model on several different but complementary inputs. And that's kind of the key intuition. So it's quite a simple idea. Ensembling is super common, across all machine learning areas. And a lot of the most traditionally best models and most flexible things are built on the intuition behind ensembling or weak learners. So random forest would be one, auto boost, any version of boost, any variant of boosting. And this just kind of works. It's a little bit magic, but it works, and it's a well-established technique. So we thought maybe we can apply it here as well in a different sense. So I already explained what traditional ensembling is. In dynamic ensembling, note in this image, the model is the same, but the inputs are distinct. So in our use case for news clustering, each of the inputs would be a distinct article about the same event. And then after we collect the output of the model on each of those distinct inputs, we need to put them together. So in the current work, we just average them, which is kind of the standard thing to do in ensembling, but you could think of arbitrary reduce functions that do smarter things, like weight different inputs differently or that kind of thing. And we may do that in future work. Let me try to give you a quick demo just to do it. So this is what the data set looks like, one of our data sets that we use. What I'm showing is one cluster of articles. So this is a cluster of articles about a terrorist attack. And there's a whole bunch of them. They're all about the same thing though. And so I've already got I just dropped a breakpoint in the code. And so I got the model ready to go. I'm going to run it on my CPU machine. Normally this runs on a GPU, and hopefully it's going to work. And I'm going to ask it to generate a summary. So now what you see clicking is it's generating the output at each time step. And those weights that you see are the weights for each input. So in this case, I only asked it to generate from 2 inputs. So at each time step, it's choosing a prediction, but the prediction that it chooses has a different weight according to different inputs. And it's going to ensemble those together. And we see the articles, but the key thing to look at, this is the gold summary. So it's a short sentence. A blast near the 11th century Dada Darpur Sufi shrine in Pakistan kills at least 11 people, half of them police officers. This is the summary generated by our ensemble model. It's quite good. So this model performs really well. It kind of passes the eyeball test, and then on the metrics that we use to evaluate this, it's good. So this is another visualization of what I just showed. On the bottom, on the x-axis, you see this summary that was generated. So each time step of the generated summary, and each row of the y-axis is a different input. So the heat map is showing at each time step how much weight that input assigned to that word. And you can think of a lot of different things that you could do with this kind of visualization. But notably at index 2, so the middle thing, I injected a noise article that's not from the same cluster. It's a real news article, but it's not from the same cluster. And we can see from the heat map that it disagreed with all the other articles. So this is also a good way of filtering noise. If you have an article that's wrong in your input, we can also deal with that. We recently at Alien released a data set for this task, which appeared at ACL. The paper appeared at ACL this year. That's what you just saw me generate a summary from. In the paper, we also evaluate on several different ones, but this is a big one, a large scale one with thousands of clusters, each quite large. So many of the clusters are over 100 articles. So this kind of mimics the real world use case. You can check that paper if you're interested, and the code is in data sets also available. So only one slide of results, but the thing to observe is that it's good. It beats the baseline, so that's what we, I guess, care about. And usually in summarization, extractive models tend to beat abstractive models. They have a bit of an advantage in many cases, but we even outperform the extractive models. So this is a pretty good result. To be fair, there's not a lot of work on this task, and this is a new data set, so I'm sure other groups will come along, or maybe will come along and improve on these results a lot. But I think it's a good start that we can beat the established extractive baselines with this relatively simple model. This also shows, however, that the multi-document summarization problem as it's currently posed is maybe too easy. So that could be another issue. And that I'm sure that's something that we'll need to look at in the future, is to create data sets that are more difficult, maybe with more noise, or with articles where the model needs to compose the information in the article in smarter or richer ways to make a more challenging task. Okay, so just for future work, there's lots of other problems that are established in NLP. Since I work in machine translation, the most obvious ones to me are machine translation related. So multi-source machine translation, where you have inputs from multiple languages. For example, you have the same sentence in French and the same sentence in German, and you want to use both of those to translate into English, would be one use case. Multimodal machine translation is another use case. So this is where you have an image or a video and a caption in one language, and you want to use both the image and the caption to translate. So the intuition is that the image could inform the translation better, maybe help you to disambiguate ambiguous words in the source language, etc. I'm sure there's many other applications of this. And then scaling up to more documents, just bigger and bigger. The scale of this is effectively unlimited. I mean, if you imagine something like the news that's generated each day about coronavirus, if you wanted to summarize all of the news in the world into one coherent summary, you would need a model that can really deal with a huge input space. So I think this is really an interesting problem for people who are more on the applied science side to look at, and it's something that we're currently looking at Alien. So I think that's it. Yeah, that's my talk. The code for this is all available, and the paper's available. It hasn't been published yet, but we'll submit it somewhere, I'm sure, relatively soon. And you can always feel free to email me with any questions or comments or anything like that. Thanks.
Cool. Great talk. Thanks for that, Chris. So a couple of questions there. Cahill Horn is wondering, and this is possibly before your particular models, but it's where, what are you using any transformer models to do the clustering? Are you using embeddings, for example, to identify similar topics? or is that just part of the sort of the standard kind of alien news classification tools?
Yeah, so in our product, in the News API product, we have a proprietary clustering, which is generating clusters. But for those data sets, if you're interested in the exact details of how the clusters are built, you check the paper. But it's a distance between documents. So the seed of the clusters in the evaluation data sets are human created. So in the Wikipedia current events portal, you see a summary, a human written summary of the event, and then you see a few links that the human user posted as references to that summary. So we crawl those, that's how we get the seed. And then we scan through the Common Crawl. We scan through Common Crawl looking for similar articles using a document-based distance metric. And if they're within a threshold, we add them to the cluster. So that's how the data set is created.
Cool. The Cathal also asks whether there's a trade-off with the size of individual documents, i.e. do larger documents result in poorer summaries, and is there a limit or ideal size for a document to be summarized?
I think that's a big problem actually with the summarization task right now as it's currently defined, is it's really underspecified. I mean, it depends on what you want to do with the summary. For some use cases, you might want to just generate a headline, for example, from a very long document. But for some use cases, you might want to make sure that you generate all key information. So right now, the best we can do is try to generate summaries that look like the gold summary in the data set that we're using for training and evaluation. And for each, if you check the paper, you'll see that for each data set that we evaluate on, we actually have to change the hyperparameters because the different data sets contain, their average summary length is quite different across different data sets. So I think this is actually it's a kind of a blocker in summarization research as it currently stands right now, that the task is quite underspecified. So I guess the answer to that is you need to know what you want to do with the summary before you can answer that question.
I know with more extractive summarization like TextRank, I know it's very popular for that. You used to specify the number of sentences that you wanted to be in your summary, right? Is there a similar sort of parameterization of the output in an abstractive?
Yeah. Yeah, I mean, I went through it fast, but in the demo that I gave, there was one of the hyperparameters that I put in was how long I wanted the summary to be. So that I put it at 64 words. But that's just something that you have to set, and that's a hyperparameter that in practice needs to be tuned for each data set.
Sure. Okay, cool. Chris Forster asks, how do you measure accuracy of the generated summary? So I guess this is beyond the eyeball test. What's the approach to evaluation?
There's a metric called Rouge, and there's different variants of that. That's the standard that's used in the research community. There's many issues with that type of evaluation. But effectively, you're trying to match the summary that you generated with one or more gold summaries. So the better it matches, the better a summary it is. So it's kind of like it's not just accuracy. You have some ability to, for example, generate synonyms, and you'll still get points for that. But more or less, it's matching. You try to match the gold, and the better you match, the better you are. There's a lot of issues with that too. A good summary, depending on the task, you could evaluate summaries in a variety of ways, but Rouge is the established way to evaluate summarization right now.
Okay, cool. So we have a number of other questions, actually. Take a breath. So he says the output's very readable, but are you sure the important facts or features are being given the correct priority? So he calls out, perhaps ethnic aspects might be particularly important in a story.
Yeah, the short answer to that is no, we're not sure at all. But the longer answer is, that's a good thing about multi-document summarization, is that now you have multiple documents that are effectively voting on what's important. So our intuition is that if a lot of documents say it, it's probably important. And in the single document summarization, you don't have that voting type of semantics where a single document might repeat the same information multiple times, or it might put it closer to the beginning if it's more important. There's other heuristics you can use and that are used. But when you have more than one document, you know a lot more about what's important and what's not. But we do observe all the time, for example, when a terrorist attack happens in the world, news articles will say different numbers of people are killed. It's very common, especially at the beginning, as it emerges that more and more people were affected by the attack. It's common for drift to occur. So That's a very difficult problem. I think it's a really interesting one, fact checking and verification. The multi-document use case may help with that, but it certainly doesn't solve it.
Sure. So this is, I guess, touches on conflicts and how to resolve that. And were there any particular, did you get into that kind of work, kind of semantic conflict resolution as opposed to actual conflict resolution?
No, I mean, that's outside of the scope of this work, but I do think it's really interesting. And I think fact checking and verification is a super interesting and important space. So, I mean, I think models at the end of the day have to do what humans do, which is go look for reliable sources that incite evidence. So, there's data sets for that, and there's a lot of groups that are working on it. But that's kind of outside the scope of this current work.
Sure, yeah. So there's a European project actually that some of our colleagues in Adapt are involved in, Provenance, which is looking at just that. So it's looking at sources of documents and I guess the credibility or reliability of the source.
Cool.
Yeah, so there's a few others here. So Reza asks, would such models work for scientific articles, like summarizing papers?
I think so. If the papers are about the same thing. A different summarization problem is take the sections of the paper and try to compose a summary from those. So that would be a harder problem where you would need like the multi-document aware model. If, for example, you had the separate inputs were like section 1, section 2, section 3 as separate documents, our model wouldn't do well in that case because we really need things to overlap in content. So that would be another example of like a different definition of the summarization problem.
Sure. Okay, and then Nishta adds then, would the model be applicable to legal documents such as contracts, consent forms, and so on? I guess it's
as long as the content overlaps a lot between the inputs, it should perform well. If the inputs don't overlap in content, then this approach is too simple.
Okay, great. So, that's it, Chris. Lots of people saying great talk. So,
cheers.
Super fascinating, interesting talk. Thanks for that.
Thanks. Cheers. Thank you.
Okay, so last but not least, we've Sebastian Ruder from DeepMind. And so thanks again to Chris. And if you can hand over the microphone to Sebastian, that would be great. Okay, Sebastian, it's all yours.
Sure. All right. So thanks a lot for having me. It's really cool after having attended some meetups while I was in Dublin to be able to present virtually now here. So I'll be talking to you today about transfer learning across languages. So how can we transfer information on to do well on languages that are different from English or from other languages people in NLP typically work on. And in particular, I'm going to be trying to give you an overview of the state of the art in this area and where current models do well on and what problems they may be struggling with. And in particular, I found it useful to motivate transfer learning across languages from the general perspective or in the general context of overall transfer learning in NLP. And transfer learning, which Chris briefly touched upon in his talk, is generally useful if you have some tasks that share similar forms of information or that require similar knowledge. And similarly here in terms of multilingual transfer learning, we also know from a linguistic perspective that languages share much underlying common structure. So there's a lot we can actually try to extract from one language and try to leverage for a language we actually care about. And secondly, transfer learning is particularly useful when label data is rare, which is very common for many languages of the world. And kind of empirically over the last years, we have seen a tremendous amount of progress in transfer learning for NLP across a wide range of different tasks. And to just cherry pick one particular example here that has seen a large amount of progress, I'm just showing here a chart that tracks the progress on a core NLP task named entity recognition, where you have to try to identify whether a token, whether a word in a document refers to a real world entity. And just on a broader note here, it's quite interesting because the initial advances after this task was originally proposed in 2003 were mainly due to work on better word representations, whereas most of the recent bumps in performance here have been due to using deep neural networks combined with deep pre-trained models and better deep representation learning. And overall, even though I'm not going to be able to touch on all of this throughout this talk, there's going to be, we've seen a similar trend for cross-linear representations in that a lot of early work has focused on learning better cross-linear representations on the word level. And now most recently, what I'm going to be talking about today, we've seen a lot of deep multilingual models. Now, to just contextualize cross-lingual transfer learning a bit more, we can kind of categorize that within the overall transfer learning landscape in NLP. And here, I think it's useful to categorize transfer learning, the particular application of transfer learning along different dimensions. Because in transfer learning, generally, we are typically dealing with a source setting where we're trying to extract some information and apply that to a target setting that we actually care about. So we can differentiate these settings whether we're dealing with the same task, in which people have typically treated those either as adapting between different domains, such as between from news data to social media or Twitter data, or which is what I'm going to be talking about today, of adapting between different languages, but still within the same task typically. And the second dimension of transfer learning is to adapt between different tasks, where the main differentiator is either if you have label data for all of the tasks available at the same time, in which you typically try to train a joint model on all of those tasks, or if you have a lot of unlabeled data available, you typically try to learn representations on that you can apply then to your target task of interest, which is what Chris did in his summarization task. Now, I think it's very important and very useful to motivate cross-lingual transfer learning also from a societal perspective. In particular, if you've used the internet or experienced the internet in different languages, potentially even, you might have noticed that what language you use the internet in really shapes your experience online. In particular, determines what kind of informations, what kind of resources you have access to, or what people you're able to meet and to connect with online. And on a broader note, as language and NLP technology is becoming more pervasive and more widely used throughout the world, we can also see or imagine that this language divide in terms of how useful this technology is for each and everyone really depends on the language people speak. And to just give one out of a large number of possible examples here, if you're in maybe post-lockdown era in a big city such as New York and you're looking for a place to eat, you might have your map application, which you could query for restaurants in a high resource language such as English, and you're provided with a set of options. You can do the same query in different language with a lot of data such as Spanish, and you're provided with a similar set of options. And if you do the same query now in a language with few resources like Basque, you're now provided with no options at all. And so you can kind of imagine that given that this is already a problem for Basque, which is a language that is still, even though it doesn't have many resources, still spoken in Europe, and for information that is as commonplace as information about restaurants, how much impact that can have for most of the languages in the world, and for information that is a lot more critical, such as information about healthcare. And the general solution, or the main kind of paradigm that people in NLP have been using lately to train methods that work in other languages is, in contrast to classic methods, which mainly focus on doing a lot of language-specific processing, so training separate models for each language, or creating separate features and separate pre-processing for each and every language you want to apply your model to. Recent methods in the line of using deep neural networks and embeddings focus on representing the inputs through embeddings as neural network parameters, and to share these parameters across as many languages as possible. And then based on this shared multilingual embedding space, we can then apply kind of our general transfer learning formula, which has already found a lot of success in the monolingual setting. And this general formula that also Chris touched upon before generally consists of given large amounts of unlabeled data, training your embedding or representation learning method of choice from word representation learning methods such as word2vec to the latest methods such as BERT. And then given data of a target task, fine-tuning that on data of that task. Now, for applying transfer learning in the cross-lingual setting, we essentially use very much a similar formula with one additional final step. So in the first step, again, we try to learn multilingual representations that are shared across different languages. And now, given that we've learned representations that in its embedding space somehow represent words or larger semantic units like sentences in the same location between different languages, we can now fine-tune our model on labeled data of a particular language where we have a lot of labeled data in, such as English. And then, given that our model has learned some underlying alignment between these languages, we can now just apply it to data of the same task in a different language and expect that it would do reasonably well on that new language. And in practice, we can learn these representations at different levels of meaning. As I mentioned before, people have learned these representations both on the word and more recently on the contextual or sentence level, which is what I'm going to be focusing on for the rest of the talk. And if you're interested, a lot of these methods are really inspired by their word level counterparts. So if you want to learn more about these cross-lingual word embedding methods, we have a survey last year, as well as a tutorial at SEL that delve deeper into those issues. Now, for evaluating these methods, generally for, as I mentioned before, there is typically a lack of labeled and unlabeled data for training representations for these methods. Most work in this line has really sought to exploit similarities on different levels of meaning between the languages that these methods are typically applied to. And the most recent line of work really tries to learn deep multilingual representations that mainly rely on large pre-trained transformers that are trained on unlabeled data in around 100 different languages. In these models, so large pre-trained transformers are state-of-the-art in the monolingual setting, and with a few adaptations, also have achieved state-of-the-art performance in different multilingual tasks. However, the main one big caveat is here that the evaluation of these methods has mostly focused on a small set of mostly classification-related tasks, and typically looked at favorable conditions, meaning languages that are very similar to each other from a linguistic perspective, or focusing on similar domains. And now the main question for the work I'm going to present to you now is whether these state-of-the-art methods actually generalize to a more diverse set of languages and tasks. And to that end, we've introduced a new benchmark suite of multilingual NLP tasks called Extreme. Where we've aggregated NLP tasks spanning 4 core categories of meaning that require different levels of reasoning. And in particular, I've put here these different tasks roughly sorted based on the complexity of natural language understanding that might be required to solve them. And after evaluating these models on the task, we can then obtain a combined score that roughly represents a model's cross-lingual generalization ability. And as we can see here, these tasks cover essentially many core categories of NLP tasks, from maybe simpler tasks that require the model to make a judgment between pairs of sentences, to tasks where they should provide a prediction on the token level, like the named entity recognition task that I mentioned before, to tasks where models have to find similar sentences across different languages, to more complex tasks such as question answering. Now we've selected these tasks to fulfill a number of different criteria. In particular, we've sought tasks that are difficult for current models, but easy for humans to solve. We've required tasks to be diverse enough, so to require representations that capture different forms of semantic or syntactic knowledge. We've also focused on tasks that can be trained efficiently, so that don't have huge training data sets in practice, so that practitioners who might be interested on working on particular low resource languages and might not have a lot of compute would still be able to evaluate their models on these tasks. We've also emphasized tasks that already cover a lot of different languages from different language families. And finally, prioritize tasks that have a permissive license so that they can be easy to share and to build on them in practice. And in terms of languages, we've sought to strike a balance between having languages that have enough unlabeled data available to learn useful representations, while at the same time having a broad coverage of different language families. And as a result, Extreme covers around 40 languages from 14 different language families that altogether use 12 different scripts. And the scenario that we focused on for evaluation here is what I already briefly touched upon in the beginning, which is known as zero-shot cross-lingual transfer. In particular, we take a model that was pre-trained on multilingual data in different languages, and then fine-tune that model in the second step on English data of a particular task of interest, such as sentiment analysis in this example. And in the evaluation phase, we now zero-shot transfer that model to data of the same task in the other languages. And in practice, the nice thing about this framework is that in our experiments and in previous literature as well, we have not observed much catastrophic forgetting of these models through this second fine-tuning step. So even after fine-tuning them on data of a particular language, these models still cover a lot of multilingual information that is ultimately useful for doing well on other languages. And secondly, and perhaps more importantly, it's quite computationally efficient, this evaluation setup, because we only need to train models once for each task and can then evaluate them on all other languages in the same task. Now in our study, we've evaluated a number of state-of-the-art models, which all together are basically variants of BERT, of a large pre-trained transformer that was itself trained on around 100 different languages on data from Wikipedia or Common Crawl. And in addition, we looked at the impact of, if you have a translation system available, of either translating data from the target language to the source language and training on that, or translating your test data to another language, as well as using multitask learning on data from different languages. However, just for brevity here, and to give you a brief overview, I'm going to focus on the performance of the best performing model, which is XLMR. So a very large transformer trained on large amounts of multilingual data. And to give you just a snapshot of the performance here, you can see a chart where for each of the different tasks along the different categories, I've put in a data point for the performance on each of the different languages sorted by the language families here, where for each task you can see with a red star the human level performance, typically at the top, and typically just below that with a golden cross, the performance on English as a language. And based on this kind of overall snapshot of the performance, we can already make a couple of observations. In particular, for many of the easier tasks, the model on English achieves close to human level performance. But on the more challenging question answering tasks, even the performance on English is actually quite a bit further away from human level performance. Secondly, in general, we can find a substantial gap between the performance on English and the performance on other languages. And in particular, the spread of the results across different languages is smallest for the easier sentence level classification tasks, and generally a lot larger for both the token level and the retrieval or question answering type tasks. And this was maybe expected for the more complex tasks, but somewhat surprising to us for the somewhat easier token level prediction tasks, because even with small amounts of monolingual data, they can be you can typically achieve quite high performance on them in a monolingual setting. However, in this zero-shot transfer learning setting, the model really seems to be struggling to transfer more syntactic information across different languages that might have different syntax or different word orders, for instance. So this is still quite challenging, even for current state-of-the-art methods. Secondly, we can also break down the performance across different language families. And what is apparent here is that the performance is generally highest on Indo-European language families, so typically languages that are spoken in Europe that have usually large amounts of resources for pre-training available. And performance is generally lower for either languages with much fewer resources, such as languages from Africa in the Niger-Congo family, or languages with different scripts spoken in Asia. And kind of to summarize here, one main insight is that generally, in particular for languages with different scripts or morphologically rich languages, tokenization, so how your model, your tokenizer splits up the individual words in each language, really is a very, still very big challenge. And in particular, if languages are, if there is not a lot of pre-trained data available in such languages, they might be underrepresented in the vocabulary, or the model might not have learned well how to segment or separate the meaningful units in those languages properly. And to just give one particular example of a morphologically rich agglutinative language, which is Turkish here, you can see a word in Turkish that corresponds to an entire sentence in English, and below the actual morphological segmentation as well as the tokenization by BERT. And we can see here that BERT actually gets the actual morphological segmentation completely wrong, in that it is not able to split up the word correctly in its corresponding morphemes. And so consequently, it might not be able to model the meaning of this phrase well as well. Now, if I've piqued your interest and you want to work on multilingual NLP or evaluate your methods on the same on this benchmark, we have a leaderboard that is publicly available for people to submit their results on. And we've also built on Hugging Face transformers to provide a number of scripts that can be easily used to fine-tune your models of interest for that task. So to take your pre-trained transformer model and to fine-tune that on different languages for this task. And in particular, to incentivize more research on low-resource languages, we've also open-sourced translations in many low-resource languages for the task we've been looking at, which can be used for analyzing the output of your model. And yeah, so lastly with that, I want to say thank you for your attention, and this work would not have been possible without these awesome collaborators.
Great, thank you, Sebastian. Super talk. In terms of questions, Koppelhorn, do we understand what are the common parts of different languages which these generally trained models learn? And was this a surprise that it learned these building blocks? Shall I do that again?
So the question was, what are if the models can learn common parts of different languages?
Yeah, or do we understand what are the common parts of different languages that the models are learning on?
Yeah, I mean, so generally, the analysis of these models and what they're learning in practice is still very much an active area of research. What people have noticed generally is that if you have languages, if you're transferring from languages that are similar enough linguistically, that have similar attributes or belong to similar language families, your model would do better on those similar languages. But for these large models that cover like 100 different languages in the embedding space, we know that the model is somewhat able to cluster related languages in the embedding space. But beyond that, beyond just like having similar kind of average representations or similar embeddings that are close to each other in the embedding space, we actually do not have a good, more fine-grained knowledge which parts, whether like syntactic, semantic, or particular like linguistic attributes of those languages, which ones the models are actually covering.
Mm-hmm. Okay. George Sturpu asks, how do you choose the right size of a multilingual model if you have a rough idea of the required capacity for each language-specific model?
That's a great question. So generally, there's a trade-off for these multilingual models between the number of languages that you want to cover in them and the capacity or the number of parameters of your model. So people have noticed generally that as you expand the number of languages that you're covering in the model, the overall average performance in all of those languages of your model goes down kind of consistently, because each of those languages will only have a smaller part in the overall parameter space of your model. So if you really care about doing well on like a small set of like 10, 15 languages, then probably the size of these models. So generally for the current architecture like XMR that I described, there actually the sweet spot is around 15 languages that you cover with about 24 transformer layers, after which the performance of the model decays. But current models already support around 100 languages at somewhat worse performance, but for the increased benefit of making it useful for a lot more languages.
Cool. Saurav Gupta asks, is human performance not measured for the retrieval tasks, as we see models trained on Germanic languages perform the best?
Yeah, it's a good point, a good observation too. So for the retrieval task, actually, because generally the way the task is framed and the way we evaluate it here is basically that given a sentence in the source language, like English here, the model needs to retrieve the corresponding sentence in the target language from a large pool of around 100,000 languages. And actually measuring human level performance on this exact task, so asking humans to retrieve a sentence based on from 100,000 sentences is it's not very feasible. In practice, there could be you could try to simplify that task for humans, so already allow them to like have a model, maybe give them a short list, and then humans select that, or simplify the task in some way. But simply because we didn't have this exact task to be possible for human annotators, we chose not to include the human level performance here.
Okay. And Hokamp asks, did you compare XLMR to laser? Was that evaluated?
In this case, we actually did not. So for context, laser is another multilingual sentence representation method that has been trained, in contrast to these other methods here, on translated data between different languages. However, what I didn't show here is that we also compared it to a model which was trained on quite similar data to laser. So the massively multilingual NMT model from Google that was trained on large amounts of translation data. So in practice, I would expect kind of the performance of that model to have similar trends or similar results to the laser model in terms of what task it does well and where it's on. But we actually haven't run those experiments.
Yeah. So how did your XLMR model compare to the massively multilingual data sets that you mentioned?
For the experiments, XLR still performed best. So as we've seen, if you just care about having these pre-trained representations that can be useful for a downstream task, actually just having a model that was pre-trained on like really large amounts of data in different languages, not necessarily translations, actually works surprisingly well. And the only method that performed better than just using these pre-trained representations was in fact translating data to like using Google Translate or some other translation service to additionally create translated data that can also be used for training. But in practice, if you have an application that you care about, if you have some data in a high resource language or in some particular language that these models are covering, like English or another similar language, then it's usually a good baseline to take one of these pre-trained models, fine-tune it, and then apply it to your target language.
And Sebastian, did you look at multilingual word embeddings such as Muse?
So also for brevity here in this paper, we did not look at them, but we had an evaluation and a comparison with them in a previous study where we found these multilingual representations to generally basically across all tasks except for the easiest ones to outperform these multilingual word embeddings. However, I think there's still a lot of interesting work to be done for these multilingual word embedding based methods, particularly because they're very easy and efficient to use in practice. And I think they can be a very good starting point for bootstrapping or for learning your multilingual models, as they already give you kind of a good anchor point in your embedding space.
Okay, there's just a few more from Surav Dutta. Also, pre-training is a very important step here. Is wiki or common crawl data good enough to pre-train the model for future downstream tasks?
Yeah, so I mean, it's a good question. So it depends what you mean by good enough here, I guess. So for current purposes, it seems to, well, at least for our current the current results and the current languages that we are focusing, we have labeled data available. The results seem to be all right. However, I kind of imagine or would guess that for languages that are very much underrepresented in Common Crawl or Wikipedia data, where data in those corpora would be likely a lot poorer quality. We also consequently, if we have labeled data for those languages for evaluation, we would consequently also see poor performance. So I think the main challenge really here is to make sure that we balance or having better ways of obtaining additional data for languages which are currently underrepresented in our data resources, or on the flip side of that, developing methods that can do more with fewer pre-trained data.
Okay, thanks. And James Barry asks whether the per task classifiers in Extreme are fixed, so that only the pre-trained model varies, or are people allowed to use their own classifiers which just have different inductive biases?
So sorry, can you repeat that, Declan? You're breaking up or getting a bit quieter.
So James asks, are the per task classifiers in Extreme fixed so that only the pre-trained model varies, or are people allowed to use their own classifiers which have different inductive biases?
Yeah, so Extreme is basically open to whatever model, whatever data you want to train your model on. So there's no real restrictions in terms of the amount of pre-trained data you can use. However, we require just to have a kind of a common playing field for people to just use the English data at this point for fine-tuning your model. But you could have classifiers with different inductive biases, different even ensembles or different forms of information that you try to incorporate in your model.
Okay, and finally then from, I think, Morgan, do you think that a new tokenizer algorithm may be built with lower resource languages in mind for better model inputs will be important in pushing multilingual performance?
Yes, yeah, I think that's definitely a desideratum. I think here something like a key feature that I mean, I don't even think just the tokenization, but I would hope that in the future, more models will also be created with low resource languages or simply other languages in mind. So not just with focus on English as a morphologically poor language. And I think this is particularly relevant for tokenization, as we've seen here, which in practice also in other papers has been observed for this subword tokenization or different subword tokenization methods, at least, to not very well align with the real morphology at all.
Okay, so Sebastian, that's all the questions. And as per the other speakers, there's lots of people saying thank you for your talk, and I would echo that as well. Very interesting, engaging talk. I should have said Sebastian used to be a colleague of Chris's in Alien a number of years ago before moving to London. So there's an additional connection there. So thanks again, Sebastian, and to Chris, and to Kavya from Facebook at the beginning of this evening's talks for 3 really engaging talks. And thanks also to all of the machine learners who tuned in tonight.
Thank you.
Cheers.
Cheers. Thanks a lot. Great talk, Sebastian. Great to see you too.
All right. Cheers, folks.
Bye.
Bye.